Hey there, y'all. In this video, we're going to study the forces on an object which is on an inclined surface. So the question for today is, how do we analyze the forces of an object if the surface that it is on is tilted? So examples of this might be something like a car on a steep driveway, it goes up a hill or something like that, or moving something up or down a ramp. For example, you may have sometime in your life pushed something up a ramp. So if you're moving and you got a real heavy box, you may have to push it up a ramp into the moving truck or whatever. And so the general picture would look something like this. Here's our surface, and then horizontal is the dashed line. And so the surface makes an angle, which we'll call theta, relative to the horizontal. And there's our box. So if we consider the forces acting on this box, some of them are going to be the same. Like for instance, gravity always pulls us downwards. But some of them are going to be a little bit different. Remember that the normal force exerted by the surface is always perpendicular to the surface. That's what normal means, perpendicular to a surface. If you push something up a ramp, it'd be pretty silly not to push it straight up the ramp. So the push force in this case, the way I've drawn it parallel to that surface. And then friction would also be parallel to the surface. So what you might kind of note right away is that all those forces are either parallel or perpendicular to the surface with the exception of one. The exception is the weight. The gravitational force, which is always downwards, is not parallel or perpendicular to the ramp. So that's going to be an important thing to realize moving forwards. So just moving my the free body diagram that I drew over here, the next step in analyzing these forces or finding the acceleration of this box would be to resolve all the forces into x or y components and then write net force equations for each direction. Now here we have two options. If we didn't learn any differently, we'd probably choose the harder option, which is to leave x and y to the right and up, and then resolve the frictional force, the push, and the normal force into components that are parallel and perpendicular to that coordinate system. Well, that's going to be really hard because you're going to have to do 3 vector diagrams, and then you're going to have an acceleration in both directions because this thing would accelerate up and to the right or down and to the left. And so option 1 is not a very good option. So there's option 2. If we turn the coordinate system, our x and y axis, to match the surface, in other words, make x parallel to the surface and y perpendicular to the surface, like that, then the only force that we would have to resolve would be the force of gravity. So the trick is, instead of making our coordinate system up and to the right, we're going to match the incline. So option 2 is going to be our preferred option here. So how do we resolve the gravitational force? We kind of consider just the force of gravity, like that. We can figure out the angles that would be in our vector diagram. So this angle here, theta 2, would be 90 degrees minus the angle with horizontal, the gray angle. I'm going to leave that as theta. If I kind of extend that line a little bit, and then draw a line that's perpendicular to the surface, remember that's what we want our components to be, is perpendicular and parallel to that surface, that line makes a right angle with the surface, meaning that the angle in between the force of gravity and the dashed red line that I drew has to be theta, since theta 2 and theta have to add up to 90. And so, when we resolve the force of gravity, we're going to set up our vector diagram such that that angle theta is part of our vector diagram. So kind of drawing a little bit bigger down here, force of gravity still goes downward. The y component of gravity would be the part that's perpendicular to the diagram, so that would look like that. And then there's my x component. So you can see it still makes a triangle, which our vector diagram should. The right angle of our triangle, oops, get the right pin, is right there. And then that angle right there at the top is the same as the angle that the ramp makes with horizontal. So these angles are the same, and that's important to remember. Kind of taking you one step further, if we can't see that, the long side of the triangle would be this side right here, making that the hypotenuse. This side is the adjacent side. This side is the opposite side. So even though our triangle isn't turned to where the y and x axis are parallel and perpendicular to like the lines on our paper, the hypotenuse is still the long side of the triangle. And so we need to be able to kind of turn that in our minds a little bit. So if I wanted to know what the y component is, I could use the cosine function. If I wanted to know what the x component was, I could use the sine function. What might make it slightly easier to visualize is if you took the diagram that we drew, the one that looks like that, we could take that whole thing and rotate it so that our x and y axes are pointing up and to the right like we're accustomed to them being. And so when we do that, now we can kind of see how the frictional force, normal force, and the push are parallel and perpendicular to our coordinate system. The only one that's not is this one. And so again, when we did our vector diagram, we got a component that did something like this, and a component did something like that. So let's look at a simple example. Suppose we have a 2 kilogram box which is at rest on a surface. And then let's suppose the surface is inclined at a 37-degree angle from the horizontal. And we want to know what are all the forces acting on this thing. So the first step would be to draw a free body diagram. So there is my surface. There's the force of gravity, always goes downward. Normal force is perpendicular, so it'd go up and to the right, or excuse me, up and to the left like that. And then friction would be holding this thing up the ramp. It's not allowing it to slide down, so friction must go up the incline, and friction's always parallel to the surface. So there's my free body diagram. The force of gravity, that should be easy. Just multiply by g, the mass by g, that is. And so we would get something like 20 newtons. And then don't forget to indicate the direction. The right direction is down. The next step would be to write a net force equation in each direction. Net force in the y direction, so remember y is that way, perpendicular to the surface, would be the normal force minus the y component of the weight. And in the x direction, remember that way is x, we've got friction minus the x component of gravity. Since this thing's at rest, I know that both of those net forces are 0. And so I know that the normal force and the y component of gravity have to be balanced. And I know that the frictional force and the x component of gravity have to be balanced. And so resolving the weight vector, y component and x component, 37-degree angle goes at the top. And so I can use the sine function to find FGY. So FGY would be FG sine 37 degrees. And so 20 newtons times the sine of 37 should be something like 12. And so the normal force will be equal to 12 newtons. And then don't forget to indicate the direction. So the normal force is perpendicular to the surface. And that's kind of all we really need for the direction on something like that. So take a minute and see if you can pause this and figure out what the force of friction is. So when I did it, I got the force of friction to be about 16 newtons up the incline. So again, don't forget to include the direction. Let's look at another example. So kind of a similar setup. We've got a 50 kilogram box which is being pulled up a ramp by a cable. Cable is kind of like a rope. And we know the ramp makes a 37-degree angle with the horizontal. That gives us nice sine and cosine values. And that the tension in the cable is 600 newtons. We also know that the force of friction on the box is 200 newtons. So we're going to kind of do this. You do part of it, check yourself, and then I'll give you something else to do with it. But the first thing I want you to do is just press pause and see if you can draw a free body diagram showing the forces on this thing. Press pause, see if you can do that. So my free body diagram would look something like this. Gravity goes down, normal force is perpendicular, tension is up the incline, and friction in this case would be down the incline. So since the box is sliding up, friction would oppose its relative motion, and so it would go down. So next, do this. See if you can resolve the force of gravity. Again, press pause, see if you can do that. So the triangle will look something like this. That angle right there is 37 degrees. Doing m times g gives you 500 newtons for the force of gravity. And you might recognize that that was a 3, 4, 5 right triangle, or you can use your sine and cosine. Either way, you get FGY to be 400 newtons and FGX to be 300 newtons. So do this now. See if you can take the free body diagram and the vector diagram that we did and see if you can use that to find the acceleration of the box. Again, press pause, see if you can do it by yourself, and then press play again. Hopefully you could write a net force equation in the x direction. And so the net force equation will look like tension minus friction minus FGX. So tension goes up the incline, friction and FGX goes down the incline. So plugging in the values give you something like 100 newtons. That would be the net force on this object. And then we know Newton's second law, acceleration is equal to net force over mass. Not sure why there's an equal sign there. And so plugging in your net force of 100 newtons, and then the mass is 50 kilograms, will make the acceleration 2 meters per second squared. And again, don't forget about the direction. So the acceleration's up the incline because the net force was up the incline. So let's kind of summarize the things we need to remember. If you have an inclined surface, then tilt your x and y axis so that they are parallel and perpendicular to the surface. So x is parallel, y is perpendicular. Resolve your weight into the components, perpendicular and parallel, so that they're x and y. And then we need to remember that when we draw the triangle for FG like that, our vector diagram, that top angle is the same as the angle that the surface makes with horizontal. You can remember those three things and do everything else we've learned about forces so far, then you shouldn't have any trouble understanding and analyzing an object which is on a surface that is inclined. So until next time, ta-ta.